Nuclear reactor physics is the physics of neutron fission chain reactance system, and this is a core discipline of the field of nuclear engineering. Nowadays, nuclear reactor physics deal with the basic physical principles governing the behavior of the nuclear reactor, which are well understood. The most of basic nuclear data needed to nuclear reactor analysis have been measured and evaluated, and the computation methodology is highly developed and validated. It's now possible to accurately predict the physics behavior of the existing and future nuclear reactor system under normal operation conditions. This course is designated to introduce students to the range of concepts, ideas, and models used in the nuclear reactor physics. It was the best for the future study on nuclear theory of reactors, methods of experimental studies of neutron fields, students' research work. The course is based on the classical course Neutron transform theory, which has been taught at National Research Nuclear University MEPhI during the last 20 years. After studying the course, the students should be able to define basic processes that may occur in the reactor core, laws, equations, and limits of applicability of models describing the neutron field in the reactor, demonstrate the practice experience of calculating the distribution of neutrons in the media, demonstrate the ability to analyze the process of slowing down neutrons in various media typical for nuclear fission reactors from the standpoint of understanding the physics of the process. Evaluate important reactor parameters, including performance and safety. As additional sources to discover information for best learning, you can see here. Please pay attention to first and the last references. The materials of the course is closer to it. The last materials is available in different language. The learning of course material demands the acquisition in math and general physics in accordance with first and second years of any technical bachelor education program. You need to be introduced in basics of integration, first and second order differential equations, vector algebra, and the math analysis. You need to know the basics of atomic physics, but no special knowledge in nuclear and reactor physics is needed. Nuclear reactor physics is the application of nuclear physics. That means the behavior of elementary particles and nuclear energy is taken into consideration in this course. The nuclear energy comes either from spontaneous nuclear conversations or induced nuclear conversations. Conversations are associated with mass and energy changes. By the modern data, there are more than 100 elementary particles, most of them with antiparticles. The particles can be divided into two parts: particles without inner structure, fermions, quarks, leptons, bosons, and composite particles, hadrons, baryons, it means the protons, neutrons, and mesons. Since the atom nature proof in 1803, it was believed that atoms are the elementary particles. Discovering of radiation indicates that there are subatomic particles. An atom is the smallest constituent unit of ordinary matter that has been properties of a chemical element. The following notation is used to define the nuclear reaction. Z is the atomic number, number of protons. The N, neutron number, number of neutrons. A, mass number of atomic nucleus. A equals N plus Z number of nucleons. The nucleus is the small, dense region consisting of protons and neutrons at the center of the atom. The isotopes are the variant of the atoms with a different number of neutrons. Electron was discovered in 1897. Proton was discovered soon after electron. Charge of proton is the same in magnitude but the opposite in sign to an electron. Neutron was discovered in 1932. The mass of neutron is closer to mass of proton. Two nuclear particles can interact together. As a result, two or more nuclear particles or gamma rays are produced. Nuclear particles can mean nucleus or nucleon. You can see the long and short formalism of description of the nuclear reaction, where A is the target in the rest before reaction and B is the projectile. For example, oxygen bombardment by energetic neutrons. It's sufficient to note four the fundamental laws governing these reactions. Conservation of nucleons. The total number of nucleons before and after reaction are the same. Conservation of the charge. The sum of the charge on all the particles before and after reaction are the same. Conservation of momentum. The total momentum of the interacting particles before and after reaction are the same. And the conservation of energy. Energy, including rest mass energy, is conserved in nuclear reaction. Nuclear physics required for nuclear reactor operates mostly with nuclei and the neutrons. Energy of individual reaction is small, therefore it's convenient to use special energy unit, the electron volts. Mass of atomic scale is expressed by atomic mass unit, mu. It's by definition 1/12 of the rest mass of an unbound atom of the carbon-12. The Avogadro number expresses the number of elementary entities per 1 mole of the substance. We need to know the quantity of nuclei in the medium. For definition, the quantities describing material properties, we use the atomic mass is the mass of special isotope, can be expressed relatively in atomic mass unit. Mass weight is the average mass of the atoms of the element expressed in mu, and the molar mass is the mass of 1 mole of substance. It's important to determine the quantity of atoms per nuclear per volume unit, designated as N capital. And by definition, we need weight density of the substance multiplied by Avogadro number and divided by molar mass of molecule of a substance.